let's see if we can have more participants than after the first lecture. Okay, let's stabilizing. Okay, then let us start then. So, good afternoon, everyone. Welcome to the NITheP Mini-School. My name is Francesco Petroccione, and I'm the interim director of NITheP. And today we have the second lecture of Amira Abbas. And just a very brief introduction of Amira. Amira is a PhD student in my group at KZN, and she's also already won many prizes and awards from many of the leading quantum computing companies in the world. I don't know if I can mention them, if it is a hidden advert or not. But anyway, today she will speak. She'll give us the second lecture, which is about data encoding and essentially about state preparation for quantum computing applications. And before I ask Amira to share the screen, I just wanted to announce that we implemented a threat that we expressed during the last lecture, and that is that many of you asked us to issue certificates of participation, yeah? And we thought we'd do it a little bit challenging, so that at the end of the webinar, a quiz should pop up on your screen. And if you answer more than half of the question correctly after today's lecture and after the following lectures, we will then issue the certificate of participation. This is an experiment. We do it all for the first time, so maybe it won't work, but hopefully it will. Yeah. So Amira, if you would like to start sharing your screen, while you do that, I will remind people to use the Q&A facility to ask questions. And like during the last lecture, Dr. Sinaisky will moderate the questions. And if there are urgent questions, we can interrupt Amira and allow her to comment and do the necessary explanations. So Amira, please, we already see your first slide. Thank you very much. And we are very curious to see to learn what you are going to teach us today. Thank you.
Cool, sure. Thank you so much, Francesco, again, for such a nice introduction. Yes, so welcome back, everyone, to the second week of this mini school, which hopefully after this, you will be able to code up a basic quantum machine learning model on your own. And today in particular, we'll be talking about how to get classical data and information into a quantum computer. So I think this is probably the most frequently asked question that I receive from people, especially people in classical machine learning and in computer science. In order to do quantum machine learning, and the way we define it, in the last lecture, we defined it as classical data that's processed on a quantum computer. The first step is fundamentally how do we even do this? How do we get classical data into a quantum computer so that we can build a model like a classifier or a neural network or something like this? So hopefully we will answer this question today. Okay, so just a reminder, previously what we covered in the last lecture was an introduction to variational circuits. So these quantum circuits that depend on some parameters. We built a very simple 1-qubit model, and then we optimized this model using PennyLane. And today, what I want to talk about is some data encoding techniques, and then we will also create circuits, and I will show you how to implement these encoding techniques, again using PennyLane, but also using another software framework that's open source called Qiskit. And again, if you have any questions, please feel free to go ahead and ask them. Okay, so let's begin getting data into a quantum computer. So historically, there are a lot of papers, a lot of research out there that try and do things like state preparation, right? So what does that mean? Well, state preparation is basically some sort of quantum routine, some sort of quantum operations that try to prepare a target quantum state that is desired for a particular algorithm or for a particular computation. And so I've just listed a few papers over here of examples for different state preparation algorithms, state preparation routines that are quite famous, I think, or quite common. And I'll make these slides available on the NITheP website, so you don't have to worry too much about writing anything down. But specifically, when we talk about encoding classical data, so the state preparation routine is more general, but when we talk about encoding classical information, yes?
I still see your input slide, and it's not
okay, so it's not
mode.
Okay, thank you for telling me. That's weird. Let me stop and share again. So let's
okay, now I see agenda.
Yeah. Now do you see full screen?
No. Okay, somebody
yeah, we can see the agenda.
You don't see
but not a full
screen.
screen.
Yeah.
Do you see my cursor, my mouse?
Yes, we can see your cursor.
Okay, let me try and do full screen one more time. Otherwise, we can just keep it like this. Okay, does it work now? Oh, no. Wait.
But it's big enough, Amira, don't worry. Yeah.
This is very strange. Okay, so you just see the agenda and it's not in full screen. Okay, well, this is gonna have to work. Okay, let's just go with this. Yes, so the first step, getting data into a quantum computer. So I was talking about state preparation routines, and these are the papers that I mentioned of some examples that exist in literature that, that prepare general states for an algorithm and for computation. But specifically, when it comes to encoding classical data into a quantum state, state preparation is a little bit more unique. And some examples of state preparation routines that encode classical information are listed here in papers. And some of these techniques are more, I'd say, more popular. So we will go through things like basis encoding, amplitude encoding, angle encoding, and higher order embedding. And these are examples of how to encode classical information into a quantum state for machine learning. But there are also other methods out there, and some of them are very interesting. So I put another one here that's a variational approach. So we studied variational circuits in the first lecture. And what this paper essentially says is that how you encode classical information into a quantum state can actually be learned. It can actually be trained using a variational circuit so that when you encode information, you optimize it with certain parameters around it. So this is, I thought, was quite an interesting idea. And I encourage you to go and read it. It's a very nice paper. But for the purpose of today, we'll cover techniques in increasing order of popularity, I'd say, for machine learning. So basis encoding, probably the least favorite for quantum machine learning with variational architecture. And then amplitude encoding, second least favorite. And then I think angle encoding is probably one of the most popular methods. And now recently, these higher order embedding techniques are being increasingly studied, and they're quite cool. So we'll talk about them as well. And lastly, what I want to also just highlight is that this is still very much an open research question, right? So while these are some proposed methods for encoding classical information into quantum states so that we can use them, this is still an open question as to why we should use a certain method for a certain data set, what methods work well for certain data, for certain models. And I don't think we have full clarity over what we should do and when we should do it. So this is still an ongoing research question to figure out how to ask. Okay, so basis encoding. So basis encoding, remember, when you have quantum computation or a quantum circuit, you have basis states in that circuit, right? And so basis encoding, as the name kind of spoils and reveals, is basically trying to encode information into these basis states. So the first requirement is that your data needs to be binary. So you need to have a binary representation of your data. So let's say we've got some binary data set where each data point, so this M data points, belongs to this data set, and we can write every data point as a binary string. Then we can encode our data set into some quantum state by literally writing into the basis states or representing the basis states as our binary strings. And if that doesn't make sense right now, it will probably make sense with a simple example, which we'll do. So basically, you want to create a superposition of basis states, and these basis states must correspond to your binary data. So if we take a very simple example, let's say we've got two data points. I write them x1 and x2, and they are binary strings of the form 0, 1 and 1, 1. What basis encoding says is that we need to prepare some circuits such that we have quantum states that correspond to these binary strings. So these are basis states, and these basis states correspond to our data. So if we had 2 qubits in our system, in our model, and we put these 2 qubits in uniform superposition, then what we'd get is we'd get an equal probability of all possible basis states with 2 qubits, right? So all possible basis states in this example are just 0, 0, 0, 1, 1, 0, 1, 1. And if we had to look at the amplitude vector associated with this quantum state, 2 qubits in equal superposition, it would look like this, right? Because there's equal probability of getting each basis state. But we don't want this. What we actually want is something representative of our data, right? We don't want 0, 0, and we don't want 1, 0. We do want 0, 1 because that's our first data point, and we want 1, 1 because that's our second data point. So we actually want to create a quantum state with equal likelihood of this basis state and this basis state corresponding to our data. And the amplitude vector would then look like this, because we'd want 0 likelihood associated with this basis state and 0 likelihood for this basis state and equal likelihood for our data, the ones corresponding to our data. So it's quite intuitive what basis encoding tries to do. And then if we had, for example, so we can write our data as this quantum state here. So then if we had, let's say, data with that required high precision, right? So high dimensional data set. And now we can write it as a string of binary zeros and ones. So x1 is 0, 1, 0, 1, and x2 is 1, 1, 1, 0. We'd need more qubits to represent this state or this data. So if we had 4 qubits and we put that into uniform superposition, but we don't want that, right? What we actually want is an equal superposition of these 2 data points, these 2 basis states. We want our data to look like this. We want it to have basis states that correspond to our binary data. So you can see 0, 1, 0, 1, this basis state corresponds to this data point. And similarly, this basis state corresponds to this data point. And we want equal probability of these 2 things. And if we had to look at the amplitude vector then, because we have 2 to the 4 possible basis states that we can have, right? We have 4 qubits in our model. So we have 2 to the power 4 possible basis states that we can have. And if we look at the amplitude vector, well, then it starts to become very sparse, right? Because we only want in this quantum state things that are associated with our data. So in this case, that's this basis state and this basis state. Those are the only non-zero entries in the amplitude vector. So with basis encoding, as soon as you start to go into high dimensions, you require more precision with your data and encoding it, then your amplitude vector becomes very sparse. And I note here that sometimes the schemes to implement these basis encoding techniques, so the actual quantum circuits and the gates that you have to apply, are not always very efficient. So this is a very nice paper that you can go and read, where they implement a very nice scheme to do basis encoding. It's rather complicated, so I avoided putting it into today's talk, but if you're interested, go and read about it. And the nice thing about basis encoding is that it gives you the most freedom to do computation afterwards. So once you've encoded your data into these basis states, then you don't have to worry too much about what you do after that. You don't have to worry about your data your quantum states being destroyed or interference or bad things that can happen in certain other cases. So, but like I said, basis encoding is not really very popular, and I think it's largely not so popular in quantum machine learning because of these inefficient schemes and the limitations on hardware that we have today. So another another method that I want to talk about is amplitude encoding. So very much uncreative names here, right? So as like basis encoding encodes classical data in quantum basis states, amplitude encoding encodes classical data into the probability amplitude vectors of quantum states. So again, let's do a very simple example. I see a question. Shall we take it?
No, because it's just a question. Will the lectures be available
Okay.
online? I'm just typing down.
Okay. Okay, cool. Oh gosh, I can't close this. Okay, so yes, back to amplitude encoding. So now we can, again, assume a very simple example where we have two data points. Again, I call them x1 and x2. But in this case, amplitude encoding does not restrict your data to be binary. So we can have like floating point values, which are typically normalized, right? And I actually don't think I normalize these values. But anyway, just imagine that they're normalized, and this example makes sense. So now what amplitude encoding says is we are going to associate the values of the data into an amplitude vector for some quantum state. So since we have two data points with two entries, we have four numbers that we want to encode, right? And so we need an amplitude vector that can encode four numbers. So if we have two qubits, then we can have exactly this amplitude vector that we want. So, and typically there's some like normalization associated with this amplitude vector. But basically all an amplitude encoding method says is that instead of writing your information, for example, into the basis states, you can write it into the probabilities associated with these basis states, into this coefficient here. And in our case, we have 4, and so the probability vector would look like this. And what I want to just point out, so this is not so crucial in understanding how this technique works too much, because again, I think this is not a very popular method as of late. But what I want to point out, that's something that's quite convenient and quite nice, is that this technique, this amplitude encoding technique, it encodes 2 to the n elements, right? And n is the number of qubits that you have in your model. So in our case, we have 4 numbers that we wanted to encode. So we just needed 2 qubits. But in general, if you want to encode a lot of information, let's say 1024 data points or entries, right? Elements, then we'd only need 32 qubits. So really amplitude encoding takes advantage of the exponential growth in the Hilbert space that you have to encode information into these amplitudes. So just by adding qubits to your system, you can encode exponential amounts of data or entries. So this is really quite a nice advantage and something unique to quantum computing. So this is a different technique.
Okay.
Yes.
Sorry, Amira, can I ask a couple of questions?
Sure. Yes.
Yes. So one is about the amplitude encoding. How close is amplitude encoding to quantum Fourier transform? The first example is too close to the Hadamard gate basis state on a single qubit. What other gates are involved when it grows? Thank you. Something like QFT for phase estimation or something like that.
Yeah. I actually don't know. I don't know the answer. So I don't know how close these two things are. But I can find out and we can talk about it next lesson. I do think they are quite closely related because I do remember reading something about this, but I'm not so sure because with amplitude encoding also there's no really, there are some defined routines. I think you can also read about them in the templates that we'll discuss with the coding. But the templates that do the encoding and the embedding for quantum Fourier transform, I think are a little bit different. So yeah, I'm not too sure.
Okay. The second thing is that there is obvious typo on your slides, which you see right now, because 2 to the power 10 is equal to 1024, not to the 2 to the power of 32.
Ah, sorry. Yes, you're right.
Okay.
Good catch. Yeah.
Okay, that was pointed out by somebody else. Sorry. So now the question is about the previous way of encoding. So the basis encoding is simply amplitude encoding with 0, 1 amplitude instead of floating point numbers.
The basis encoding, can you say that again? Basis encoding is basically?
So is basis encoding is simply amplitude encoding with 0 or 1 amplitudes instead of floating points numbers? I think the answer is yes, up to normalization. Not 0, 1, but 0 and normalization.
But is it though? Because I mean, your data is encoded differently, right? I mean, you can be represented in binary form in different ways, no?
No, but I think it's a question about this basis encoding, about not the amplitude, but the basis encoding.
Okay. Okay.
Yeah.
Okay, let's move forward.
Okay, let's move on because I think, yeah, we can move on.
Sure. Yeah, okay. So the next one that I want to speak about is angle encoding. So this is something that I use, I think, quite a lot. Oh, sorry, can you, I think my connection is a little bit lagged, so I only hear you after a few seconds. Okay, anyway, I will operate under the assumption that you can all hear me correctly. Okay, so angle encoding.
Yeah, it's fine.
This is the most, I think, intuitive method to me, at least, and probably one of the most popular in the variational forms of quantum machine learning models. So I want to spend a little bit of time on this and then explain why I think this is such a cool way to do things. So quite intuitively, what angle encoding says is, again, the name reveals itself, is let's encode classical information into rotation. So you have qubits and you rotate these qubits, and the amounts or the angles that you rotate these qubits by is equal to the value of your data. So if we look at an example, so now I write the data points a little bit differently, right? They're still vectors, I just wrote them differently. And again, let's just assume we have 2 data points. And so what you can do to implement this in a quantum circuit is really quite trivial. So if you have 2 data points, and in this case, our data has 2 features, right? So they've got 2 entries. So I call these features in machine learning. And if we have 2 features, well, then we can encode them with 2 qubits. And the convention is to start by putting these 2 qubits into a uniform superposition. So we apply Hadamard gates to each of them. And then we apply rotations to these qubits. So to the first qubit, we can apply some rotation. As an example, I just chose an RY. And the value at which we rotate this first qubit by is equal to the first feature value in the first data point. And then on the second qubit, we do another rotation, in this case an RZ rotation. And the value that we rotate here is by the second feature value of the first data point. So we encode our first data point into these 2 qubits by applying rotations equal to their values. And then quite similarly, we can do the same thing for the next data point, right? We can do another set of Hadamard gates, and then we can encode the second data point with rotation values equal to each feature value of the data. And so then, like, quite simply, if we have more data in our system, so let's say we had a third data point, then we can do exactly the same repetition, right? We just do another set of Hadamards, and we do, again, these rotation values equal to the data. And then also quite nicely, if we wanted to encode high dimensional data, so data with more features. So now instead of 2 entries, our data has 3 entries, then we could just add another qubit to our system. So instead of 2 qubits, we have 3 qubits. So the number of qubits can be equal to the number of features. And then on our third qubit, we encode the third feature for each data point. So this is quite a nice, easy, intuitive strategy to encode some information into a quantum state. And I write here some advantages about angle encoding, right? So obviously it's very simple, it's intuitive, it's inexpensive. So the number of gates that you have don't grow exponentially with the number of data that you want to encode. Then also a very recent paper that came out very nicely explains the expressive power of this kind of associated with this kind of data encoding. So they show that even with this simple strategy, a very nice class of functions arise that come from the quantum circuit. So the quantum circuits can approximate very nice class of functions by this data encoding strategy. And how you choose to do this angle embedding, so how many times you repeat this or what rotations you choose, affects the class of functions that your circuit approximates. So this is quite a nice result. So even though it's simple and it's intuitive, the power of these models the expressive power is still quite high. Okay, and then I want to liken this whole idea of data encoding to something called quantum feature maps. So quantum feature maps are also very popular in quantum machine learning. And I just want to explain the intuition here. And then we'll talk about the last type of data encoding and then go to the code. So this idea is very much stolen from classical feature maps, right? So feature maps that come up quite a lot in classical machine learning, and specifically in algorithms like support vector machines. And what feature map functions do is they say, we have some data that exists in some space, typically a low dimensional space. So for example, here we've got 2-dimensional data. So every data point can be represented as some vector with 2 entries. And if we plot the data, it looks like this, right? And where the yellow data belongs to a certain class, let's say class 1, and the purple data belongs to a different class 0. And so what a feature map function says is we need to transform this data. Why do we need to transform this data? Because this data is not linearly separable, right? So typically you want to be able to separate 2 classes with a very easy function, with a very easy model. So an example of an easy model is a linear model, right? But you can't draw a line through this data such that the 2 classes are separated. You can't draw a line to separate the purple dots from the yellow dots. But if you map this data to a high dimensional space, so you apply a feature map function to take your original data and map it to a high dimensional space, so from 2D to 3 dimensions in this example, then you can see that the data becomes linearly separable, right? We can draw a hyperplane here and separate the yellow dots from the purple dots. And so if we had to represent this now, every data point as a vector, it would be a vector with 3 entries instead of 2. And I think this particular example is quite trivial, where we just have the feature map being the first entry is still x1, the second entry is x2, so these first 2 feature values. And the third entry is the feature values multiplied by each other, so the product of the feature values. So quantum feature maps are almost entirely analogous to this idea, right? Where you have some data that exists in some space, this classical data, and as soon as you encode it into a quantum state, you're encoding it into this possibly really large data vector, this large quantum state, that can be represented as a very, very big high dimensional vector. And so higher order embedding kind of borrows this intuition, right? And I put an example that's stolen from this paper here. So if you're interested in data embeddings and feature maps, I strongly encourage you to read this paper. It's very cool. And in this paper, they develop a very specific feature map, quantum feature map, and they argue that it has a lot of benefits. And how this feature map looks is, we'll do a very small example now. So let's imagine that we have one data point for simplicity, and this data point has 2 features, and I just call them x1, x2. So normally we had the numbers here, but I'm just gonna keep it more general. And with this higher order embedding, what the circuit looks like, what it does is it applies, again, Hadamard gates to the qubits. So we'd need the number of qubits corresponds to the number of features that we'd have in our data. So since we have just a 2-dimensional data set, then we're just going to use 2 qubits. We put them in uniform superposition, and then we apply RZ rotations, again, equal to the feature values. So on the first qubit, the first RZ rotation is about an angle equal to the first value in our data point. And the RZ rotation on the second qubit is equal. And then the crucial difference with this higher order embedding, the reason why it has the name higher order embedding, is there's also an RZ rotation about an angle equal to the product of the feature values. So there's an encoding of x1 times x2. in the circuit. And these are just C0 gates to generate some entanglement between the circuit. And so also if you want to build something like a more expressive or more powerful circuit, then they conjecture that repeating this feature map, so again with the same data point, encoding it more than once, they conjecture this type of encoding to be classically hard to simulate. And especially hard when you start to increase the number of features in your data, because when you start to increase the number of features, then you start to increase the number of qubits, and then also the pairs, the products of every possible feature with each other needs to be encoded. So this very quickly gets a bit tricky to do. Okay, so now that I've showed you a few examples of how to encode information, or how to think about encoding classical information into quantum states, I want to show you how easy it is to actually code it up using PennyLane and using Qiskit. So I want to.
Sorry,
yes.
Can we have a couple of questions?
Yes, sure.
Okay, so the first question is, if we go back to the encoding with the rotations Ry and Rz, is it are they choice of Ry and Rz arbitrary?
Yes, so let me go back here. Yes, the choice of Ry and Rz are arbitrary indeed. So you can design this angle encoding, this form in anything actually. I mean, you don't even have to have these Hadamards here, but then that wouldn't really make sense, right? Because then you can just add these rotations. So really, there are different conventions and different ways to set up these angle encoding circuits. And there is a very nice paper that talks about lots of different templates. It's called The Expressive Power of Quantum Circuits. I think it's by Sukin Sim. So I can also add this to the slides, and then I encourage you to go and look at this paper. But yes, the choice is arbitrary, and should also depend on your measurement strategy as well, and the things you do after. So this is just one example, but you can define it however you want.
Okay. Are there any similarities between amplitude encoding and angle encoding?
I can hear someone drilling in your house. Are there any similarities between angle encoding and amplitude encoding? Not necessarily, right? I mean, amplitude encoding really just tries to apply rotations such that the amplitude vector corresponds to your data. Whereas angle encoding, you just have total freedom, right? As long as some rotations you do in there vaguely represent your data. So yeah, I think they're both intuitive methods, but how one applies things, I think you have a lot more freedom in the angle encoding situation, which is probably why it's so popular.
Okay, so can this technique be potentially better than embedding done in NLP/ML?
Yeah, interesting question. I mean, also like these embeddings are likened to convolutional layers and all these other like classical techniques. And I think the answer is we don't know yet. And it would be interesting to understand this and see why. But I don't think I mean, I'm sure there is some evidence for why these embeddings would be better. But yeah, I'm not sure. I think we actually have someone in our group looking at word embeddings and word2vec and wanting to make them quantum, and it would be very cool to see how these two things correspond, if they do, or if quantum can offer an advantage. But yeah, as far as I know, I'm not sure. I don't know.
Okay. When mapping the amplitudes to qubit states, will there be an interference and corruption of data?
Yeah, they could be, right? So that's why I mentioned earlier, with basis encoding, you don't have to worry too much about these kind of things. But with amplitude encoding, you do have to be quite careful with the types of operations you apply afterwards, and you don't want to hurt your quantum state necessarily. So you have to be a little bit more careful in how you apply your classification thereafter, and what you do. The order of the operations really do matter. So yes, there can be, and this is something to carefully consider when you design your algorithm, if you were to use that technique.
Okay. Can we discuss optimization of more than one parameter in a quantum circuit? That's I don't know.
Yes. Sure, we can discuss that. And I would say let's discuss that next lecture, because this is exactly what we will do in the next lecture. We'll define a full model. So we'll put together the piece from last lecture and from this lecture. And then we'll also talk about different cost functions. And then we'll talk about optimization of multiple parameters in that lecture. So stay tuned for next week.
Okay. And is the iteration of set of blocks mentioned in the higher order embedding is necessary for optimization?
So I don't know what you mean by necessary for optimization, but it's necessary, I think, or it's argued that it makes the model more powerful. And what do I mean by more powerful? I mean that the functions that this quantum circuit can approximate becomes more. The number of functions, let's say, that a quantum circuit can approximate increases in variety and increases in complexity, let's say this. So and there's no proof for this, right? So this is just alluded to. Let me go back to the higher order embedding. So I think the question was, is this repetition necessary for optimization? No, but is this why do we do this repetition? Because it adds power to the circuit. And I also put up a paper previously on the expressive power of quantum models, and they also explain very nicely that when you start to repeat your embedding of your data, then your quantum circuit actually starts to become this universal function approximator. And the functions that one can get out of these are very interesting. So your model basically becomes more powerful by adding these repetitions.
Okay, and the last question, which unified the question in the Q&A and in the chat, in creation of quantum feature maps, how do we know which operations to choose for parameterization of gate? For example, x1 multiplied on x2, or pi minus x1 multiplied on pi minus x2, and etc. So how we choose x1 and x2 or something else?
Yeah, that's a good question. I think if you read this paper, you'll find the answer. So I've written here that it's x1 times x2, but the actual correct implementation that they do in this paper is pi minus x1 times pi minus x2, and in fact all these values are scaled by a factor of 2. So I think the motivation is very nicely explained here, and this is just a simplification. So the actual feature map from this paper does pi minus x1 and pi minus x2.
Okay, thank you. Let's jump to the code. Thank you.
Okay. Yes, thanks for the questions. Very good. I'm glad people find this interesting. Do I have to stop sharing, or do you see now my screen changing?
No, you probably need to stop sharing and reshare it again.
Yeah.
Okay, sure, no problem. Still need to figure out Zoom properly. Okay, let's go to Chrome. Does it work now?
Yes, now we can see your browser.
Brilliant. Okay, cool. Let me enlarge on this. Actually, I think it's fine. Okay, cool. So now we spend the next 15 to 20 minutes just going through some code examples, right? So I highly recommend reading the documentation for Qiskit and PennyLane. Here are the links here. PennyLane in particular is designed to do quantum machine learning with quantum computers, and Qiskit is a more general software framework. Both of them are open source. And Qiskit, yes, is also for quantum computing. And I think they're both very nice. Both have advantages in different areas and different things. And really, it's just the user preference. So whatever you prefer, I actually like using both of them for different things. So with data embedding in particular, I like Qiskit quite a lot. But with optimization, I prefer PennyLane. So yeah, I encourage you to go and play around with these things and see what you like. So we'll just do a very, very simple example with basis encoding and PennyLane, right? So I just want to show you how it's possible, and also how it's possible with PennyLane here for angle encoding. And then I want to show you angle encoding in Qiskit and this higher order feature map that I spoke about in Qiskit. And you can then play around with this notebook yourself. So this will also be made available on the NITheP website. Okay, so the first thing we do is we import PennyLane. So remember from last lecture, we imported and we call it QML by convention. And then importantly, we have to import NumPy from PennyLane because, as I mentioned, if you do some computations using PennyLane, we need to import NumPy specifically from that package so that our processing can handle quantum computation. And then the next thing that we need to do is actually import something called so PennyLane have these templates, which are really, really nice. So I want to show you quickly the website. So this is the PennyLane website. And in their documentation, they actually have embeddings here as a section. And then they tell you all the different functions that are predefined that you can use. So they already have things like amplitude embedding, angle embedding, basis embedding. For those of you who are asking about the differences and all this kind of stuff, you can go ahead and look at the source code and see how they do it. Yeah, so this is quite nice. So what we'll do is we'll use the basis embedding. So we'll have to go from PennyLane dot templates, and this is also from the embeddings. We're gonna import the basis embedding. Hopefully I spell everything correctly. No, I didn't. Templates. There we go. Okay. Then the next thing we need to do is we need to just create some data point, right, with some binary data. So I'm just going to simply just write a data point into a NumPy array. So let's just say we've got one with length 3, and we can write it as 101. The next step with PennyLane is to create a quantum device, right? So if you remember from last lecture, there are lots of different devices we can use, but I'm just going to make use of PennyLane's default qubit simulator. So we instantiate a device, and the one I'm going to use is the default qubit. And then we need to specify how many qubits we want in our system, right? So we have binary data of length 3, so we can encode this with 3 qubits because this is basis encoding. So we need our basis state to correspond to the length of our binary representation of our data. Okay, then in PennyLane, what we then need to do is we need to create a Q node, so a quantum node. And we attach to this Q node the device, the quantum device that we want to use. And this Q node basically tells us that this function here is a quantum circuit. So we need to define a circuit that takes in our data and then encodes it using basis encoding. So we now have our basis embedding function. So we can use that, we can call that. And what the basis embedding says is it takes in something called features. And the features in this case is our data. And what do we want to apply this basis encoding to? What qubits do we apply it on? And because we want to apply it to our full system, so the entire range of qubits, I'm just going to say range 3. So this is saying, let's basis encode this argument here, this data, which is fed into the circuit, and we apply this basis embedding to all the qubits in the system. And then we need to return something. So if we want to see that our model actually is encoding the data as we would expect, we need to return some information so we can see that it's actually working. So let's, in this case, just return a expectation value. So we can, again, just return the simple sigma z expectation value, for example. So that's the Pauli z. And we can return it on the first qubit. And then actually, let's just return it for all. It's probably a more sophisticated way to do this, but let's just do it for the first qubit, the second qubit, and the third qubit. Okay, so now that we have this circuit, this quantum circuit defined, which does basis encoding, we can check that our circuit is actually doing what we think it's doing by passing it in this data. Yeah. So if we do that, poly z invalid, what did I do? Ah, this is supposed to be 2. Okay, so if we do that, we get these sigma z expectation values returned. And does this make sense? Well, let's see, right? We get a sigma z expectation value of -1, and -1, this sigma z expectation value corresponds to a state, to a quantum state 1, right? So that is exactly what we want, because our data, the first entry is 1. Then we get a sigma z expectation value of 1, which corresponds to the 0 state, which is correct. And then lastly, -1, which corresponds to 1. So it is doing what we think it's doing. So if we had to change this to all 1s, for example, then we should see sigma z expectation values all equal to -1. And we do. So yeah, I mean, it's trivial, but it is possible to nicely encode some data using this basis embedding function in PennyLane. Okay, and then very similarly with angle encoding using PennyLane, we can do almost exactly the same thing. So with angle encoding, remember, we don't have to restrict our data now to binary strings. So I am going to first import a very well-known data set, which I'm sure many of you know is iris. And then we'll also need some additional functions. So we'll need this shuffle function, which basically just shuffles your data around. And then we'll also need some sort of normalization. So we'll need to normalize our data after we import it. So I'm just going to use sklearn's normalization function. I think it's from preprocessing, if I'm not mistaken. And then we can import normalization and then use this, well, it's just called normalize, and then use this later. And then we need to set a seed. The reason we set a seed is just to reproduce our code, just good practice. np.random seed, and I'll just set that. Okay, what am I doing wrong here? Normalize. Okay, I think this is fine. Okay, so the next thing then is to actually load the data. So we've imported iris, and now we want to load it. So what we do here is I've just called our data X and our targets, so the classes associated with this data Y. Use the shuffle function to shuffle the data around, because when you import iris, it imports it all in order of the classes. So you have all the data for class 0, then all the data for class 1, and all the data for class 2. So we actually just want to shuffle this around. And then we want to pick a few of the entries. So for simplicity, let's just pick the first 5. And let's also pick the first 5 of the targets. Okay, and then we can print the data. And now we just have 5, right? We have 5 data points, and these are the classes associated with this data point. So like I said, we need to normalize this data. So we can do that using the normalize function. And we want to normalize our data, and then let's print it and see what our data looks like. Okay, cool. So again, we have 5 data points and they are normalized. Okay, so now that we have some data and they're normalized, we can now use PennyLane's angle encoding template to embed it into a quantum state. So again, we need to import the template specifically associated with angle embedding. So we can go from PennyLane templates and embeddings. We'll import angle embedding. And now more generally, I just want to define the number of qubits that we need in the system. So remember, for angle embedding, the number of qubits that you need typically equals the number of features you have in your data. So in the iris data set, there are 4 features in the data. So I'm going to specify the number of qubits as 4. We create a quantum device, as we did before. And now this time in the circuit, we have to do a little bit more operations. So angle embedding first does Hadamard operations, right, to every qubit. So we can do that by doing a loop over all qubits. We can say for I in range And how many qubits do we have? Number of qubits. We can say apply a Hadamard to every qubit, to qubit I. Then after we do that, we can use the angle embedding. And the angle embedding takes in arguments similar to the basis embedding. So there's features, we pass the data in. And the wires that we want to apply this to is again the full range, right? So we want to apply this to all the qubits that we have in our system. And then again, I return some sigma z expectation values of every qubit to see if our information is actually being encoded. So now let's pass in one data point into our circuit and see if it actually worked. So let's just take the first data point, right? So remember, our data is defined as these 5 data points here. And if we pass in the first data point, basis, what did I do wrong? Let's see. 1, 0, 1, 2, 3, 4. Basis state parameter must be an array of 0 and 1 of length at most 3. That is very strange. If anybody knows what I'm doing wrong, please feel free to point it out. And okay, I see. I think I see. No, okay. Well, don't worry. I've got a plan B. I have done the notebook already at home, and we can run all of these again.
Yeah, one of the participants just said that you didn't run one of the pieces of your code.
Okay, cool. Which one is that?
I think not where it failed, the one above it, maybe.
Okay, let's just start again. No, unfortunately, wait, this.
Okay.
Unfortunately not, right? Weird, works now. Very strange, okay. I'm not sure how I fixed it, but it does seem to work now. Oh, so they're probably right. I just probably didn't run something in order or was missing something. So thank you for whoever pointed that out. Okay, so if we look at the sigma z expectation values of all the qubits, then basically all of them are 0, right? And why? Well, this is actually a cool thing to note, is that angle embedding, the default rotations that it applies using your data values is Rx rotations. And if you do Rx rotations, then when you do sigma z measurements, then this does not affect the sigma z outcome, right? So we can actually specify the rotation to a different angle. So let's say we specify the rotation to y. And then if we run this again, then we get very different outcomes, right? So our outcome, our sigma z measurements are no longer just 0, our sigma z expectation values. And we can also then like change the data point and see we should get slightly different expectation values every time. So this is a very trivial example again of how to use angle embedding with this PennyLane template. But what's important here is the type of rotation that you choose based on the measurements that you do. And also this was just for one data point, right? So we just wrote a function that can encode one data point. But if we wanted to encode all the data, then what we actually need to do is, I'm just going to copy this and paste it here. We need to create another loop over our data set. So we can go for I in range, and we're going to iterate over the length of our data. And then we're going to apply angle embedding for every data point. And then we return the expectation value again. So if we do that, run that, and now we can pass to the circuit the full data, and we get sigma z expectation values that encode the full data. Okay, so that was with PennyLane, and now I want to show you why I prefer actually looking at Qiskit for this particular type of data embedding. So with Qiskit, this is the first time we're using it in these talks, but I'll use it again next week. There exists a circuit library in Qiskit. So you can go ahead and look at all the different types of circuits they have. They already have predefined templates, very much like PennyLane. And in there are a whole bunch of feature maps that are already designed as circuits for you to use and for you to append things to and chop and change and manipulate. So I'm just going to import everything from Qiskit, and then in particular, I'm going to import the feature map that we want to look at. So it's from Qiskit and circuit library. And I'm going to import the angle embedding feature map, which is called the Z feature map. I hope this is how it's called. Let's see if that works. Okay, I think that should be fine. And then once we import the Z feature map, we can now use it. And it's beautifully simple to use. So we can create like some sort of, we can call this thing a feature map circuit, and we'll use the Z feature map. And the arguments it takes is just how many qubits you want in your model. So again, we want 4, right? Because there are 4 features in the Iris dataset. And then you can tell it how many times you want to repeat the feature map embedding. So remember I said, if you repeat the structure, then it should, in theory, become more powerful. But let's just, for simplicity, use 1 repetition. So we're not going to repeat it. We're just going to have it encode once. Reps. Okay, so now we can print this feature map circuit. And this is something I like very much in Qiskit, is that we can actually print the circuits that you create. So now after printing this straightforward angle encoding, we see exactly what we want, right? We see 4 qubits, and in these 4 qubits, we apply header mods, and they encode via some rotations that depend on these values, on x0, x1, x2, x3. But these values are, we haven't really told it, the circuit, what they need to be equal to, right? So it's not attached to our data, our information yet. So these are just kind of like dummy variables in this feature map circuit. So we need to actually assign to the circuit the data values that we have in the Iris data set. So we can do that by creating, let's say, another circuit object. I call it circuit, and we'll encode the first data point. And we can do that by taking this feature map circuit and using this assign parameters. So we can assign parameters. So these are the parameters in the circuit. We can assign values to these parameters. And in this case, we want to assign the values of the first data point, for example. And then if we print the circuit, let's do that. Then we can see that the values in here are equal to the values of the first data point, and they're scaled by 2, so it's 2 times the values. If we just remove that scaling, then we can see exactly the first data point being encoded like this. So we've now attached the first data point, and then if we wanted to attach a second data point, then we can simply like combine. We can use something called a combine, and we can combine multiple circuits in Qiskit quite nicely. So I'll show you very quickly how to do that. We can create, let's say, another circuit called, I call it circ data 1, not very creative names. And then what do? Well, we use the previous circuit that we just defined, and then we combine it with the feature map, the original circuit that we have. But this time, we're going to assign the parameters of the second data point. And so if we print now this circuit, then we have our, let me divide this by 2. Then we have our first data point encoded and our second data point encoded. So we can stack data points like this. So more generally, a more efficient way to do this is to simply like just define a quantum circuit. This is from Qiskit with 4 qubits, and we can write a loop over the entire data set, and we can say for I in range length of the data. We want to create the circuit that combined with the feature map circuit where we assign it parameters for every data point at every iteration. And then if we print this final circuit, and then let's scale this, then we can see that this loop went over every data point and encoded it exactly like we wanted. So this is a very nice way to attach your data and your information and visualize it using Qiskit. And then lastly, the high order feature map, I know I'm running out of time, is also very, very simple. I'll just show you very quickly. It's called the ZZ feature map in Qiskit. And we can do almost exactly the same thing we just did with the Z feature map. We can call on it as a function. Oh, let me run this. And we can define how many qubits we want. Let's just say we want 2 qubits and we don't want to repeat it. Just want that. And then if we print this feature map circuit, we can see it is the high order feature map where we've got the first feature value encoded, second feature value encoded. And then remember, I told you there was some products of these feature values. So you can look at the third rotation is pi minus the first feature value and pi minus the second feature value multiplied by each other. And yeah, then you can go ahead and attach information to the circuit. And we will discuss next week how to do models, then how to build on this and incorporate variational classifiers into this after we've encoded information. So thank you for listening and sorry for going over time.
Amira, thank you very much for a very nice talk. I really enjoyed listening to it. We had already lots of questions, but Ilya, I'm sure there are a few more.
In fact, right now there is something is coming. Okay, yes. Does PennyLane have a function for printing a circuit structure as a Qiskit?
Yeah, so I was actually looking for this, and yeah.
Yeah, go on.
Okay. I was looking for this recently, and I think they wrote in December that they were going to implement something like this in their new version, in the new update. But it was not obvious to me on their documentation if they have this. So I'm not sure if it's a feature that's coming, but I think there is a way to print circuits that's very similar to notation used in how they do it on Circ, for example. So that's Google's quantum language. So I think they probably do, but it's not so straightforward. Like with Qiskit, you just print these objects. So I think this is quite a nice advantage.
Okay, so there is one more question. So we can encode whole data set with thousands of data rows.
Yeah, so can we encode lots of data? So there's only so much that the simulator can handle, right? So I think after a certain number of data with a certain number of dimensions, you very quickly run into speed issues, even on the simulator. So especially once you start like doing quantum operations after the data encoding. So I've tried, I think, up to like 100, 200 data points of like maybe 4 to 10 features, and this is perfectly fine. But I think once you go higher, then you probably run into some problems.
Okay, and how would measurement outcomes of these techniques be useful?
Okay, let's see. Oops, sorry.
Sorry, Amira. How would measurement outcomes of these techniques be useful?
So measurement outcomes, if you remember, I spoke in the last lecture, will depend very, very much. They link very closely to cost functions. So your choice of cost function. So how you define your measurements or what measurement strategies you want to use they go into the design choice of your entire quantum machine learning model. So I think let's discuss that in more detail in the next lecture, but really the answer is it depends. So if you're going to do a bunch of X rotations in your model and measure on a different basis that doesn't make sense for these rotations, then you're not going to get information that's meaningful to you. So really you have to bear in mind how certain measurements are affected by certain rotations, and how do these things come together end to end. And then your measurements also then go into the notion of a cost function, which you eventually want to minimize. So these things are all design choices, and they're something that one as an engineer needs to be cognizant of.
Great, thank you. And some anonymous attendee give you a hint on the PennyLane, saying that you can use print and in the bracket circuit.draw. So you can try.
Okay, great. Okay, cool. I knew there's a draw function in Qiskit as well, but I didn't know that PennyLane has it. So that's great. That's good. That's really beneficial. I find these drawing functions really quite useful. So thank you.
Okay, thank you.
Okay,
Cool.
if there are no more questions, Amira, thank you very much again for the very nice hands-on lecture. I'm sure everybody will play around with Qiskit and PennyLane later today. And now there is the big question whether the quiz that we prepared for you will work. And in theory, when you leave the webinar, after you press end, you should be automatically directed to the page with the quiz. That's the theory. So let's hope it works. Yeah. So Amira, thank you very much again. Ilya, thank you for the question, and thank you to all the loyal participants. And we will be back here next week again at 2 o'clock. And I think next week Amira will speak about variational circuits, if I remember correctly. Yeah. Okay, wonderful. Thank you very much. Have a good rest of the day. Bye-bye.
Thank you.
Bye. Thank
Bye-bye.
you.